so it's a pleasure to announce Urs Frauenfelder from Augsburg University. He will give a mini course on non-local homology. And today the first lecture is on Morse and
Thank you very much, and thank you for organizing this conference. Yeah, it's a bit a funny conference because I think people from quite different sides come together, and yeah, it will be probably a bit strange how a eternally neutral symplectic geometer gets interested into Weber dynamics, but and the story is also a bit longer. So I think today we start very calm with Morse theory, and so this is basically we are interested in critical points, and then later on critical points will become periodic orbits in Hamiltonian system. That's then the connection to Kai's talk. And then we can also ask what happens if we have force laws which are not local but depend on the past, and then we will get connection also to Weber dynamics. But today is just critical point, and today I would like to talk about Morse homology. So we have M is a closed manifold, and F from M to R is a Morse function. So that's a smooth function with the property that all critical points are non-degenerate. So i.e. if X is a critical point of F, i.e. fx is 0, then we can look at the Hessian of f at this point. So we have the Hessian of f at x, so the Hessian, and the kernel of this Hessian, this should be 3. So basically you can understand Morse homology on one example, and this example I will use again and again today. So this is the example of the heart. So in the heart we have 4 critical points. We have 2 maxima, a saddle point, and a minimum. And then and we assume that they are non-degenerate, so locally the function looks something like 1 over x1 squared plus 1 over x2 squared, but not something like nothing flat. And then we have the Morse index. So we have the so if x is a critical point of f, then we have the Morse index of x. This is the number of negative eigenvalues of the Hessian counted with multiplicity. So the Morse index, a number of negative eigenvalues of the Hessian x counted with multiplicity. So let's look in our example. So in our example we have here, let's call it x1 and x2 are maxima, and they have Morse index 2. So we have here 2 directions where it goes down. So we have u x1, x2, and then here we have a saddle point. Let's call it y, and here we have the saddle point has index 1. So we have one direction goes down and one goes up. And here we have the minimum. So the minimum has Morse index 0. Good. And now in Morse homology, one defines a graded vector space, and so we declare these critical points to be a basis of a vector space. Define graded vector space Cn star of f, and this is we take the critical points of f and declare it as a basis of a Z2 vector space. So this is the Z2 vector space with basis critical points, and now we have to do the grading. So in grading K, we want to look at the critical points of Morse index K with basis critical points. Morse index K. So this is a formal sum. For example, we could have the sum x1 plus x2. This is in this vector space. And we take Z2 coefficients for simplicity, but could also do it with Z coefficients. But the good thing about Z2 is that minus 1 equals 1, and we don't have need sides. Otherwise, we have to discuss sides as well. And then we have a graded vector space, and we define a boundary operator on this vector space. And this boundary operator is defined by counting graded flow lines from a critical point to another one. So we have a boundary operator. Delta, and so the index goes one down. So this is a linear map, and because it's linear, we can explain it just on the critical points. So we pick x, the critical point of index k, and we define e of x. This is the sum over all critical points, which has index 1 less. And then we count the number of graded flow lines from x to y times y, and because we are working with a 2 coefficient, we count this modulo 2. This is the number. So to see how this works, let's look in our example. We always can use the heart to illustrate all the concepts. So we see here we have from x1 we have you see here one gradient flow line from x1 to y. So we have d of x1 is d to y. And we have, we also see here one gradient flow line from x2 to y. So we have also d of x2. And now let's look also from y to z. So you see two gradient flow lines, one here in front and one below. So we count mod 2, so the number mod 2 is 0. So we have e of y, this is 2z over 2 is 0, this is 0. And now we already spot some kind of miracle. So the miracle we see here in this example is that if we apply d 2 times, d squared is 0. So that means that the boundary of the boundary is 0. The boundary of boundary vanishes. And this is what one calls a boundary operator in homological algebra. A linear map Q square is 0. And if one has such a gadget, then one can define homology. And homology is because D square is 0. If something is in the kernel of D, it's automatically in the image of D. Because if you apply, if something is in the image of D, then it's automatically in the kernel of D. If something is in the image of D, it's D of something, and D square is 0, so D of this is 0. So therefore we can define homology in the following way. So we define Morse homology H and K. This is the kernel, also gradient vector space, the kernel of delta modulo the image of delta. So maybe let's just see in the example to let's compute it in the example so you see how it's going on. So we see that x1 is not in the kernel because d of x1 is y. But if you take x1 plus x2, then d of x1 plus x2 is 2 times y, and 2 is 0. So d of x1 plus x2 is in the kernel. And of course, it cannot be in the image because there are no critical points of index 3. So we have, also in the example, and we have the degree 2 Morse homology is, I write this like this. So this is the vector space generated by this element. So this is a one-dimensional vector space. And in what happens in degree 1? So in degree 1, okay, we see the y is in the kernel, but now it's also in the image. And so because we mod out the image, it vanishes. So we have the h m1 of f. This is trivial. And now let's see in degree 0, there the z is in the kernel because there is nothing of degree -1. But z is not in the image because d of y is 0. So we have here in degree 0, we have this is generated by z. And if you look at this, if you know about the homology of a sphere, what we see here is precisely the singular homology of a sphere. So this is a way how you can define, how you can compute the singular homology of a sphere. So let me talk about why does this miracle occur, and why is the boundary of the boundary 0? This is from the definition, not very obvious. Y is d square 0. And so let us talk about this gradient equation, gradient flow lines. So what is the gradient flow equation? So we have our Morse function. To define the gradient, we also need a metric. so here we can just, we have our sphere in three-dimensional space, we have an induced metric. If you have an abstract manifold, we have to choose an additional metric. So we have the gradient. So we have the differential d of x. This is we need some Riemannian metric g on m. So then we have the gradient. So we have the covector, and you make a vector with the metric. And then the gradient flow equation is so we have an x smooth map from R to M, which satisfies the following equation: dsx plus nabla fx. Every s dsx s plus nabla fx s 0 for s. This is our gradient flow equation. So this is a first order ODE. And solutions of this equation, these are parametrized gradient flow lines. Because the picture always lies a bit, because in the picture you never see the parameterization. And here, when we have solution of this ODE, this is a parametrized gradient flow line. This is a parametrized gradient flow line. X, the solution star. But now an unparameterized gradient flow line is because we can look at time shift. So we have time shift. So if we have R with a number, so we define the time shifted gradient flow line R star X of S. This is just we change time. X for S in R. And if X is a solution of star, R star X is also a solution of star of X. So X solution of star, this is equivalent to R star X is a solution. And therefore, when we talk about unparameterized gradient flow lines, we mean equivalence classes, so modulo time shift. So if two solutions just differ by a time shift, then we call them equivalent. So unparameterized gradient flow line. X, that's an equivalence class. Solutions of star. So if I draw unparameterized gradient flow lines, so if I draw them like that, you cannot see the parameterization. To make a parameterization, what I can do the following trick. I can make here a point like that and say here we are at time 0. And if I draw like this, then it's actually this picture is a picture of a parameterized gradient. So I fix the time where we are time 0. And now so these are parameterized these are unparameterized gradient flow lines. Now curious fact that we have a boundary operator. This has to do with the compactness property of this unparameterized gradient flow lines. Now let's first look at the following. So we have M is a closed manifold, so it's bounded. And we have here, if you look at this equation, so we have the derivative. The derivative we have under control, because this equation tells us precisely that the derivative is the gradient of f, and we are on a closed manifold, so this is bounded. So if we have the derivative under control, this means so our x is what we call equicontinuous. So they cannot derivative under control, the x is under control. And then there is a famous theorem in mathematics, so this is the theorem of Arsenal, and this tells us that if you have a sequence of solutions of this equation, then we have a subsequence which has to converge. And it has to converge first locally, and we will see in how this local convergence tells us. So star and the theorem of Arsenal-Ascoli. So suppose we have x nu solutions of star and for mu in n, then there exists another solution of star and a subsequence j such that x j converges to x in infinity log. And so now, why this log? So let's see on the picture. Let's go back to the heart. We always can see everything on the picture of the heart. So let's look at the following thing. So here is again the heart. And we have, here is a sequence of gradient flow lines. And now, because this is solution of star, so here I didn't load out time shift. So here I should draw them as parameterized gradient flow lines. So I put here a point and say here we are at time 0. Then so here is our sequence x nu, and to what does this sequence converge in the limit? So it converges to this gradient flow. And now you see that it's local. So here, so it doesn't converge globally. So here the asymptotics might change. And it's even more dramatic. So if you change the parameterization of this sequence, then we can also converge to different gradient flow lines. Then we can time shift them, and so we are at 0 here, and then they will converge to this here. Different parameterization can lead to different limit. So we have now this sequence. But now I have here I'm at 0, and then in the limit I will see this. So now to get the global convergence, I just take both of them. So for global convergence, so this is, yeah, there is some debate. This is a compactness theorem or the non-compactness theorem. So if you have a sequence of now we can go back. So if you go to the broken one, this will not depend on the parameterization. So if you have a sequence of unparameterized gradient flow lines, we will have a subsequence will converge to a broken gradient flow line. So we have then global convergence. Now I draw them. I don't make a dot because there is no parameterization, and then I think you can understand what is the global limit. This is this here, this here. So the limit is a broken. Okay. And why does this compactness theorem prove that d squared is 0? So now let's look at the following. So maybe we can everything here in this example. So we have here x1, and we want to understand the square of x1. So we want to understand d square of x1. And so what's the d of x1? So these are the points where we reach with the gradient flow line, and now d square of x1. These are all broken gradient flow lines from x1 to z. So these are the number of broken gradient flow lines of Z from x1 Z. And how many broken gradient? There are of course also two broken gradient flow lines, and this and this, and we have also this, and we can go backwards. So there are two broken gradient flow lines. Here is x1, here is y, and here is z. So we have this one and this front, and then we have the other one. The first part is the same, but here we go here. So there are two broken gradient flow lines. And how can we interpret this gradient flow, broken gradient flow lines? Namely, these broken gradient flow lines, by this compactness, this is the boundary of the moduli space of all unparameterized gradient flow lines from x1 to z. So if you look at the whole moduli space of unparameterized gradient flow lines from x1 to z, these are all of this. they go once around. This is like it looks like an interval, and the boundary of this interval, these are precisely these two guys. Boundary of the space of all unparameterized. Here is this modularized space of unparameterized one interval, and then the boundary here is the orange one and the green one. The green one is if you go back. Now the deep ingredient we use here. So this here is a compact one-dimensional manifold with boundary. So in this example, you can see what this is precisely a closed interval. So this here is a compact one-dimensional manifold with boundary. Now, what kind of compact one-dimensional manifold with boundaries you know? Not so many. So what compact one-dimensional manifolds with boundary? So the interval, as we have seen in the example, so there could also be two intervals, so we don't say it has to be connected, there could be even three, there could be even some circles around, but now you count the boundary points, and there are no more. Now you count the boundary points, the circle has no boundary points, the interval has two, so modulo 2 is nothing. And so this proves that d square equals 0. So you see how this analytic statement that you have this compactness of this breaking gives rise to an algebraic statement, namely the d square equals 0. And this algebraic statement, this allows you to define homology. Okay, so we illustrated this everything on the example of a heart, and what we computed is we just computed the homology of S2. So it actually should not depend. If the computation shows that it actually should be something just depending on S2, and this is actually true. So in fact, the Morse homology does not depend on the Morse function you choose. That's a rather interesting statement. So whatever Morse function you choose, the homology you compute, this will be independent of the choice of the Morse function. So effect is, so the Morse homology is independent of choice closed manifold, it just corresponds to single homology. And let's illustrate this fact. So once illustration. So you can say maybe our example was a bit too hard. What we looked at, the heart. There is an easier Morse function on S2. So the reason why I have chosen the heart is not that it's the easiest way to compute the Morse homology of S2, but the most instructive one, because on the heart I can illustrate everything, what happens with breaking, but I could choose a much easier Morse function, namely just the standard height function, and you see here we have one maximum and one saddle point, one minimum, no saddle point. So in this case there cannot be any gradient flow line, and so by degree reasons, so there we have just the homology in degree 2 is generated by X, it's one dimensional, in degree 0 is generated by Z, is also one dimensional, and in degree 1 we have 4. So an immediate corollary of this fact are the Morse inequalities. Morse inequalities. So let me abbreviate by the kth Petty number, ek of m. This is just a dimension. So I have this homology. This is a two-vector space. So I can take the dimension. This gives me a number. And this is the kth Petty number, and I just write here m and not f, because by this fact that it's independent of the choice of the Morse function, so it just depends on m. So in the case of the sphere, it's 1 in degree 0, it's 0 in degree 1, and it's 1 in degrees 2. And then the Morse inequalities. Function. Then we have the number of critical points. They can be estimated from below. So we have a uniform lower bound on the number of periodic of critical points, namely the sum of the Petty numbers of n. And the proof with what we did is basically obvious. So we have the number of critical points of n. So what is that? So we use this critical point to define vector spaces, CNKs. So these are a basis of these vector spaces. So this corresponds to the dimension of these vector spaces. So this is the sum of the k from 0 to a dimension of m, dimension of CMK of f. Now if you go to homology, in homology we first take the kernel of the boundary operator. The kernel of the boundary operator is a subspace. So a subspace always has a dimension less than or equal. And then we mod out the image. So we might lose once more. So we can say this is bigger or equal the sum k from 0 to dimension of m, the dimension of the homology, the Morse homology, and this is just by definition the vector numbers. So these are Morse inequalities. Basically, now again. So yeah, I have a bit more time, and we will discuss more about this tomorrow. But now, so these are just for critical points. But now for these Hamiltonian systems, which Kai introduced, so an old question of Hamiltonian systems is, do they admit periodic orbits? And this question about periodic orbits, this is very much related to celestial mechanics. Namely, it's very much to the question about the moon. So the moon is more or less a periodic orbit, so it comes every month. So it's a periodic orbit of a period 1 month. And so the question is, does the moon exist? So that because the moon is tough. The moon is not easy to detect. Because the moon is attracted by the Earth and the Sun. This is not a two-body problem. It's not like Kepler. It's already at least 3 bodies are involved. So to find their periodic orbit, this is already a tough question. So this is an old story of finding periodic orbits. And we have, in symplectic geometry, we are crazy about this. So we always want to find these periodic orbits. And so we are influenced by Poincaré, because Poincaré told us we should do this. Because Poincaré told us that these periodic orbits are the only way to penetrate the stronghold, otherwise inaccessible. So in view of that, so we want to find them. And now let's do a bit of symplectic homology, like talk a bit about the Arnold conjecture. So in general, for the Arnold conjecture, we should know what the symplectic manifold is, and I think Kai will explain more about what the symplectic manifold is. Maybe today I can also give an example. But for today, because probably you're a bit tired, you don't want to learn now what the symplectic manifold is. But for today, you can think about the symplectic manifold as the torus. And this is actually historically was quite an important topic. The case where one historically first checked the Arnold conjecture. So in general, when the symplectic manifold, so M omega is a symplectic manifold. If so, omega is a two-form. A two-form on M, which has 2 properties. It's closed. It's closed, namely P of omega is 0, and it's non-degenerate. Which means that if we have x a point in M and xi a tangent vector at x in M, then we have omega. Then there exists some other vector, some other tangent vector, such that omega xi eta is different from 0. But now for today, maybe it's easier to think of the following example. Example. So the first example is we can take R2n, which makes also a lot of sense from physics. So we have here, so we have maybe Q1 up to Qn, Pn. And then omega is the sum pi matched I. So this is closed because we have here already these. So if and it's also on the channel. So this is the standard symplectic form R n. That's the standard. And in fact, it's even true that locally all symplectic forms look like this. So this is the so-called Darboux theorem. So there is a big difference between the symplectic forms and metrics. So for metrics you have local invariants like curvature. But for symplectic forms, this is so intuitively this closeness you can think of a bit like no curvature. And so because of this closeness, there are no local invariants, so we can always locally bring this to the standard form, but not globally. So globally there are a lot of invariants, but no local ones. And then if this is maybe not too physical, but I suppose now everything is periodic in these variables. Then this is the torus, and of course we have the set 2n action here on this R2n, this isomorphism. So we can look at the quotient. The quotient R2n mod Z2n. This is a torus, and this is an example of a manifold which is closed. So this R2n is not closed, and originally what Arnold was interested were more closed. Maybe that's example 1. This is not closed, and example 2 is the T2n is R2n mod Z2n. This is the 2n dimensional. Now if you have a symplectic manifold, then what is a Hamiltonian? A Hamiltonian is just a smooth function. So a Hamiltonian H from M R, this is just a smooth function. But now what is interesting, so if you have a function we can associate to this vector field. Similarly if you have a function, that if you have a remaining metric you have the gradient. But here we have not the metric, but we have this form, which is anti-symmetric. So we define the Hamiltonian vector field. X H, and this I define implicitly also by, so I can look at the DH, this is a one form, and if I plug in my Hamiltonian vector field into my symplectic form omega, I get the DH. And because this omega is non-degenerate, this XH is uniquely determined by this equation. This is the vector field. And what in Hamiltonian dynamics, what we would like to understand is the flow of this Hamiltonian vector field. For example, in celestial mechanics, we have this Hamiltonian of celestial mechanics, and if we understand the flow of this vector field, then we understand the future and the past of our universe. So that's how the planets will what they will go in future and past. So often we have also Hamiltonian which additionally depend on time, and so actually what Arnold was looking at was an example where we had a time-dependent Hamiltonian, but the time dependence is periodic. So you can think you have some force which periodically comes and goes. Morse. So we have so we have time dependent. Hamiltonian, but periodic time dependent Hamiltonian. So our Hamiltonian is now depends on an additional variable, also on S1, smooth. And so S1, this is the surplus. I will always think of the surplus arm on Z. The circle. And then if I have time t S1, I aggregate ht. This is, I evaluate my h to this time t. So this is then just a smooth function r, and so I get also a time-dependent Hamiltonian vector field. Time-dependent. Vector field. So I have x, h, and now periodic orbit. This is a solution of the ODE. So this is x. This map from S1 to M. Et xt equals x h t x t t in S1. This is a periodic orbit. And so question is, do they exist? Do they exist? And then if they exist, because this is a very general question, so we have now general Hamiltonian. So we would like to know uniform lower bounds. And now for these Arnold conjectures, because you remember the Morse inequalities, and the Arnold conjecture is something very similar to the Morse inequalities. For the Morse inequalities, we need Morse function, and so we also need here a Morse condition. And so, what is the Morse condition? If I have a vector field on a closed manifold, I also have a flow. So I have flow of x h t. So this is dt of h for t in R. This is a diffeomorphism. M, and this is defined, so d0 of h, this is the identity, and I have d of dt by h of x, this is x h t of phi th of x. So if we know the flow gives us the future of our universe. So we have here is x, and then so we have this Hamiltonian equation. So we know how we would like to know how this x propagates in future, and so so here is then phi h of x. And so here the vector field is always x, h. So if you start at 0, this is 0 at x. And so therefore, if you have a periodic orbit, a periodic orbit also corresponds to fixed points of this flow. Namely, let's call this this is our new star. Although an old star, but old star we don't need anymore. So this is our star now. So if we have x, the solution of star, this is equivalent that x of 0 is a fixed point of phi h. Over phi h is phi h1, the time one of this flow. Because if I have a periodic orbit like this, so I start here with x0, so this is x, and then I flow with the Hamiltonian vector field. This is and then I come back because I'm periodic. And now I can formulate what this means to be non-degenerate. So x solution of star is called non-degenerate. Only if, so we can now look. So we have this flow, so we can look at the differential of this flow. So we look at the differential of this flow at x0. And what is this differential? This differential is a linear map from the tangent space here of tx0 to tx0 back. So this is from tx0 m to itself. This has no eigenvalue equal to 1. It has no eigenvalue. So the eigenvalue equals to 1. So if for example, if you have a family of periodic orbits, then if you have a family, then if you go in the family direction, then you will there have an eigenvalue equals to 1. So this for example guarantees that these periodic orbits are isolated, like in Morse, where the critical points are isolated. And so now I can formulate the Arnold conjecture. Conjecture by Arnold, and it's not quite in this form, but almost. It is now almost theorem by Fleur, but by Arnold. So it's so we suppose that h times s1 r is some periodic such that all periodic orbits are non-degenerate. Then we can estimate the number, the number of periodic orbits. So these are the number of solutions of star. Right? So these are the number of periodic orbits. They can be estimated from below by the sum of the Betti numbers. So k equals 0 to m. Rather reminiscent of the Morse inequality. So before that were here I have written the points of the Morse function. Now I have here the periodic coordinates. And for example, if you look at this for the torus, this is fantastic. For the torus, if you have as a remark, what are the Betti numbers of the torus? Remark. So we have the Betti number of the dimensional torus. This is 2n over k. And if you look at the sum of the Betti numbers, n, k, t to n, this equals 2n. So this is a fantastic big number. And so for the torus, this gives you enormous lower bound. Good. Yeah, I think this is the point to stop here. And tomorrow I will explain how. So one has to interpret this as critical points. So this is kind of classically known. That is so you know that you can interpret periodic orbits as critical points of the action function. But then you have to define a homology. And for that one needs a compactness. What we have. That's what I proposed.
Okay, so that's any questions?
The conjecture of Arnold. So in this, okay, so I was a bit sloppy about the coefficients because today I always used Z2 coefficients, and with Z2 coefficients, as far as for the torus, yes, but for general, what I know it's true over rational coefficients. So tomorrow what I want to explain to you is the proof for symplectically aspherical symplectic. And there it's true with Z2 coefficients. Even with you can take coefficients in any field. But in very tough cases where you have a lot of bubbling, then as far as I know, you still need irrational coefficients. That's because of some transversality issues.
This more or less recent proof of Katrine Verheyen and students using polyphonies.
But then you also get with rational coefficients. The reason is because you need multi-sections. Because so of course this is a bit far ahead. But so we have. It doesn't make sense. I don't know. It makes some sense. So we have now we have these periodic orbits, and now we have a gradient flow lines between them. They look like cylinders. Before, so what we have seen in the Morse picture is the limit the sequence can break, and this is okay. So the cylinder can break, but in general there could be also some bubbles on it. And if you have these bubbles, then so formally the bubbling is a codimension 2 phenomenon, but to have this transversality, you need to use multi-section to get rid of this bubbles. So that's why in general one needs the rational coefficients. But tomorrow I will not do the most general case, and so tomorrow I will explain the symplectically aspherical case, and then there we don't have the bubbles, and if you don't have the bubbles, then we have compactness as in today, when we